It's too bad it's not on U.S. television. Maybe I'd be in the White House now. Maybe not. But yeah, I wouldn't protest if someone wanted to nominate me. Okay, so ladies and gentlemen, moving right along. We are going to explore some of the topics which came up in chapter 3 of the book, and excuse me, chapter 4. Excuse me, 4. Yeah. So chapter 4 was handling errors without exceptions in its name, and it began with a discussion of some of the issues with traditional error handling. Okay. Does anyone remember some of those issues discussed in the book? Say with throwing exceptions, or say with using designated return values for a function to indicate errors. Can anyone tell me? What are some of the issues?
Stops your program, and
sorry,
an exception usually stops your program.
That's right. That's right.
If you were attempting to process a large amount of data,
that's right.
Time consuming.
That's right. So that's a big motivation. An exception is handled exceptionally, and in the traditional way, when an exception is handled, it propagates upwards to a point where there's a handler for it. There's a try-catch block, for example, right? And one of the problems here is if we want to build sort of composable pipelines that handle large amounts of data, in well-defined, structured, systematic ways, it's a problem if we just pop out of those pipelines at any point, say bad thing happened in the middle of the pipeline, and we don't have an easy way of resuming it or knowing the exact context. We've got this messy situation where some of the things are processed and some are not, some may be incompletely processed, and it's difficult to handle. So that's a big motivation. That's a big motivation for the sort of functional error handling we're going to be talking about today with monads, with try and option being the key thing. What's another motivation, though? I'm going to go call up some slides here, but what's another motivation for functional error handling? Anyone? What's the problem with designated return values?
It's a side effect.
Okay, they could be implemented with side effects, but I'm talking about a situation where we might, for example, make use of let's suppose we're searching within an array for the first index that matches some predicate, some criteria. And suppose if we don't find something that matches that predicate, we return -1. What would be the problem with that? Or suppose we have a double precision calculation and we return not a number when we encounter a problematic condition. What's the matter with that? Okay, yeah, we don't know the problem. It's not really self-descriptive, is it? We're not characterizing kind of the nature of the issue, where it occurred, and in what context it happened, so that we can deal with it more effectively, right? So that's a large part of it. And there's another issue, though, with designated return values, which is, first of all, for many types, we don't have well-defined ones. So you take an example of double, for example. We have a not a number. With integers, we actually don't have a very nice sort of defined illegal number for an integer that will say this is not an integer, right? Rather, we have conventions, and we might say, for example, by convention, we will treat -1 as that exceptional thing in a context where we know we can only have things that are 0 or more. So we'll say we'll treat -1. Something like a long. This led to Winchell's utterance, which is one of the funniest things I've heard in the past 5 years, maybe 10. Last year, I asked him, like, what's a, like, okay, for doubles, we have not a number. For integers, we have -1. What might we use for a long? I said, what's the most distinguished long? And he looked at me and he said, Jeff Long. That's the most distinguished long. Jeff, for those who don't know him, is in charge of the TAs for the department. And indeed, he's a distinguished lecturer. Yeah, it was a good answer. And you might think I need to get out more if that's one of the funniest things, but it is that I've heard in the past year. So ladies and gentlemen, there's a problem because it's very ad hoc, and more significantly yet, do you remember last time we talked about type parameterized functions, for example? Remember, we could take a function, we define it, def it, and we could have it, for example, let's take the search example. We're searching in a collection for a given element. Maybe we want to generalize it so we're not just searching int collections for ints, or long collections for longs, or person collections for persons. We want a more general thing. It'll handle any of a broad set of possible types, right? How are we going to return a distinguished value, to indicate something if we have a type parameterized function? If we're returning an index, then it's one thing. But in other cases, we might want to return a unique kind of value of the type of the parameter, and we don't know how to do it because it's a different value for not a number for doubles than it is for ints than longs, and we can't parameterize it by the unique value it returns, right? So ladies and gentlemen, this is another problem that we have with these sorts of traditional mechanisms of handling errors. There's others too. We don't have time to go into. For example, exceptions are very expensive. They're expensive to throw. They're actually expensive to some degree as well to set up the infrastructure needed to handle them if they occur. So what I mean by that is they're expensive when they occur, but even if they don't occur, there's a certain amount of superstructure and so on that you're setting up just in case it happens, so you know where to propagate to and so on. So it turns out that traditional exception handling is a problem when we have large pipelines, and using sort of return values informally is also a non-starter. It's not going to get us very far. So what this chapter explores is the use of monadic ways of implementing error handling. And there's two primary constructs introduced, to wit, option and try. Okay, but within the course of this chapter, as is reflective of the book in general, and actually, yeah, he introduces either briefly as well. But in the course of this chapter, the authors do not, in fact, explicitly use one of Scala's niceties, which is an existing implementation for try. They actually, he defined his own option here and uses it to handle various cases. He also introduces lifting, and he introduces a definition of try as well, which is sort of a construct that he puts in place in the form of a function that takes a call by name thing and returns an option. He further introduces the notion of lifting, whereby you can have, well, can anyone tell me what lifting is? This notion of lifting, if we think about something like option, and we have a function that's operating on int, say, what does it mean to lift the function to operate on options events? Well, what it means is that we can basically create a version of that function without special casing it, without specially define it. If we have a function that operates on ints, we can just say lift of this function, and it will operate now on options events. Okay, and it turns out that that notion will be handy within the Spark context. Okay, we're going to be able to lift functions there to operate, to go from operating on values, say, of primitive types, say in doubles or whatever, and we're going to be able to have them operate on columns. Okay, which is very handy. Okay, now I'd like to explore these notions, but using the built-in mechanisms of Scala. And I'd like to start out by doing some imports, okay? I'd like to import scala.util.random because we're going to be generating some random values. And I'd like to import scala.util, okay, as well. Both of these are going to be quite handy in our perusings. Scala.util, amongst other things, includes try. Okay. Now, having leveraged that, I want you to remind me, if I do a vector fill of say 100, and I'm using currying here, and I say next double, what's it going to give me? What is this going to give me back? What's that going to give me back? Vector of 100 what? Yeah, different doubles. Okay, just making sure I'm being recorded here. There we go. So it's evaluating, and here we go. 100 different doubles, and this is passed by name, all by name, so that it's evaluated for each of the elements. Right? We get different values. Yeah. Okay, so it's taking advantage of laziness in a way we'll be discussing more in a coming lecture. Okay, now I want to show you something that's emblematic. It's an exemplar of the types of issues that come up quite a bit in processing of large-scale data. That's an inconvenience, okay? And it's an inconvenience that we want to be careful about how we handle it, because it's going to bear on our ability to build robust, larger programs. So I am going to fill up here 100 values with doubles. And in fact, I think to make the point more clear and brief, I'm just going to fill 10, okay? 10 values. And I'm going to filter, ladies and gentlemen, those so that we're concerned only with those greater than 0.5. So you know how to do this, right? Okay, here we go. And we can get back those greater than 0.5. Now, we haven't really discussed it, but I think it's been perhaps alluded to in the book. I'd have to check. Does anyone know how to add those up? If I wanted to add up, and we'll even do it without the filter at first, but if I wanted to add up all the elements of this array, how would I do that? Anyone know? Okay, it turns out there is a sum, and we could use sum in some contexts. So here we've added them up. Okay, great. But in general, there's actually another operator that's more general than that. You can do fold, and fold will do it in a sort of successive way. It turns out that there's a thing called reduce, which yeah, it has some differences from fold in some of its details. So here we are applying this operator, which sums things up over each of the elements. Alternatively, we could multiply them, right? This is a binary operator, and we would get the multiplication of them, right? We okay with that? Okay, now, here we go. I'm going to put in this filter thing, okay? That should work as well, right? Yeah, here we go. So we're going to multiply all those values that are greater than 0.5, right? Or we'll sum them up. Let's sum them up just in case we start having lots of them. It'll be easier to talk about. Okay, we're going to sum them up, right? Okay, now let me show you something that may be a bit disconcerting. I'm going to do it to 0.75, right? Here we go. I'm going to say greater than 0.95. All these should work, right? It's a thing of beauty, right? We have these general operators like filter, reduce, map, as we'll see, flat map, fold. And what's beautiful about it is that it's orthogonal. You can apply those with any number of different functions applied to them, right? So we can say filter by this criteria, filter by that criteria. That's in many ways their power, right? We can use the same operators with any number of different functions, just like we saw earlier with our differentiation operator, right? This is one of the things that makes it very powerful. We don't have to special case things. We don't have to write a large filter just to filter things, greater than one, greater than a certain value or what have you. We can just pass in different things. But watch this. Okay, I'm gonna keep on doing this. And now I'm gonna say, okay, and for the final one, I'll do greater than 0.99 here. Okay. And something bad happens. Something unhappy happens. Something disconcerting happens. Ladies and gentlemen, this is, sorry? No, it turns out double can handle up to, yeah, it could handle up to a difference of like 10 to the minus 32 or something. So it's not that, but it certainly is disconcerting. I mean, after all, it worked with 0.95. I wonder if it'll work with 0.975, right? What is it that's going on here? At some point, it ceases working. Anyone have an idea? Well, if you want to understand these sort of things, it behooves you to just copy the pipeline and investigate, right? Okay, what's going on? Anyone see the problem? Yeah, we're trying to add up what? Nothing. Ladies and gentlemen, we're trying to add up nothing. By contrast, if we were to do something like that, we're trying to add up, luck of the draw. Each time I'm regenerating it. So, okay, there we go. There we have some, right? So the problem is should be clear here that sometimes we get nothing. But that just pushes back our concern one more level, right? Because, okay, maybe right now for some applications, the limit is 0.99. For some, it's 0.9, beyond which we'll get nothing. We could put in a special case here. I mean, it's good to know where it's coming from. We could put in a special case. Well, if it's empty, then stop here or something like that. But you have to realize that for a lot of data pipelines, we might have many additional operators here, right? We might want to filter those greater than that, and then we want to reduce them, and we want to, you know, square the result or something, or we want to go and, you know, multiply it times something and pass it to a function. In short, if we have to interrupt anywhere along the way, just because we didn't happen to get enough numbers this time around, it's awkward and inconvenient. It gets, again, to this problem with exceptions, that you have this kind of gunk of sort of dealing with these special cases in the middle of what otherwise is a beautiful pipeline. You see what I'm saying? So there's got to be a better way of dealing with this than to sort of have to break the pipe, stop the pipeline there, ask special case, is this empty? If so, do this other thing, else, you know, continue on in this way. We'd like to be able to compose these pipelines, combine one with the other in a very general way, grow them, have a long sequence of operators applied to them. And if every time, if in many places in the middle we have to special case things, it starts to be similar to exceptions. You have all these sort of special rules for dealing with situations. So fortunately, we don't have to go that route. Ladies and gentlemen, may I introduce to you a general characteristic of Scala libraries in general, and a characteristic of the Spark libraries in particular, operators that operate on, that operate on values that or return values that are encoded with these monadic components. So here we have reduce option. Now, why is this any better? Why is reduce option any better than just reduce? Well, you could say at a naive level, okay, it doesn't die. Yeah, that's nice. If there's an error, it handles it. It handles none. But let's suppose I had something after this. I want to square the value returned, right? Suppose I set this back and I can go and I can add them up. And now I want to square it. How would I do that? How would I square this value?
A map?
Yeah, map, ladies and gentlemen. Map it is. So I could go and I could square that value, right? There we are. Now, what happens? What will I get out through that if I change this to 0.99? I'm just guaranteeing that there's, yeah, it'll just be none, right? Where did that none originate? Where did the original problem originate? Well, it originated somewhere in here, right? In other words, this thing returned an empty thing. But the rest of this is able to handle that because we're characterizing this unusual condition in a robust way, namely with options, right? And that allows us to continue writing our pipeline here in a very straightforward way without worries that something earlier has totally broken and we have to special case it. Do you see what I'm saying here? Okay, so let's continue on to so that was option, and let's just continue on to just reflect on option values. Let's create a few option values and just be clear about how they work. Okay, val. We're going to have v1 here that is going to be some value of 3. So you'll notice that when we do have a results here, like this was 0.5, we denoted it the result as some value. So this is some value, right? It happens to hold the value 3. Value v2 here equals, and we're going to say, you know, sum of well, here, I'll do none, okay? Now, we could say this. We could say, you know, that this is none. But I'm going to actually indicate very clearly that it's the same type here, just for conceptual simplicity. So this is going to be a value of option int. In Haskell, do you know what we call options of ints? We call it a what? Anyone know in Haskell? It's a maybe int. And we might have one, we might not. Right? If we do, we hold it. If we don't, we call it none here. Okay.
Do we have maybe operator?
I'm not aware that there's one called maybe here, but in Scala, the equivalent to maybe in Haskell is roughly option. Okay. Okay. So here we have V1, V2, and for good measure, I'll describe a V3. Okay, which is going to be sum of 4 here. Okay. Now, a few things about these. So one thing is that, as seen earlier, we can map them, right? V1 dot, we can ask, you know, to map it to square it, right? So say we can square this operator, or this value, and if we square a sum of 3, we get back a sum of 9, right? If we square a none, what do we get back? None, right? It's no value. So we get back no value. There's no value corresponding to it. Okay, very good. We can further ask, you know, is it empty? Here, you know, is this empty, for example? And the answer is false. For V2, is it empty? Yes, it's empty. Now, we can do a lot with just those things we've seen, but it's much more powerful than that. So, for example, we could ask this dot get or else. So maybe we want to get the value in it. Well, here, I'll show you a problem with just getting it. We could say, okay, get its value. Here we go. We are going to get, oops, mumble. Sorry? It just get. And V2 dot, now it's supposed to say V2 dot get. What do you think will happen? Yeah, we'll get an error because there's no value to get. So in general, you have to be hesitant using get. Now you could ask if it's empty, and if it's empty, then we don't get it. Otherwise, if it's not empty, we get it. But that's kind of convoluted. There's actually a thing called get or else. Okay, get or else allows you to explicitly substitute a value if you don't have it. So maybe we want it to get or else its value. Otherwise, you're oops. What am I doing? V2 dot get or else. We can explicitly substitute a value for it. If we can't get it, we use the substitute value. Otherwise, we use its value. Now, we can further apply the normal operators. V1 dot filter, for example, filter if this is greater than 2. And what will I get back if I filter this and I say greater than 2? Anyone? If I say V1 dot filter, if the value is greater than 2, we'll get back sum of 3. How if I were to instead say filter it to be greater than, I want to filter it to screen out values, include only values greater than 10. Well, I get back. Yeah. No, I'll get back a none here. If I were to do none dot, if I were to do this, what would I get back? Well, none. V2 is already none, so I get back none. In short, these are values that encode in a distinguished way. I won't opine on whether it's more distinguished than Jeff Long, but it encodes in a distinguished way whether or not we in fact have a value, a legitimate value. And it allows us, more significantly yet, to process that value in well-defined ways. Regardless of whether we have it or not, we could still complete the pipeline. We could still continue to process the value and get back results that are at some level interpretable. Okay. This is with option. Option is used a great deal to encode that we might have something or might not. And when you have these pipelines, it's very valuable. And hence you will see it in the Spark context with these pipelines we'll be using. Okay, I wanted to go to talk about this other key element, which is try. How is try different from option? What's the different notion of try here? Oh, well, actually, maybe before I answer that, I will just ask. We talked about lifting earlier. This idea of, so we have a function, say, that operates on ints. Let's say it's square. And we want to lift it, so we have a function that operates on options events. It takes in an option event and it returns an option event. Fair enough, right? The square operator works on ints, and we want a square operator that works on options events. How could we implement that? How can we implement square, a square of an option event? We actually, I would argue we actually did it. How did we do it? Suppose I have an option event. How do I produce an option event that's the square of it? What do I do? Yeah, I just map x squared over it. I use my existing operators. I just do, map, x to x squared, right? There we are. Boom. This basically applies, and conceptually, it's sort of lifting this operator, which operates on ends, to operate on options event, right? By mapping it, I am taking this function, which normally applies on ends, and I am now applying it on options events. By virtue of that, I take in an option event. I take in an option event. That's what V1 is, and I return an option event. Okay. There's other ways to lift it as well, but this is a very powerful notion that just by saying map of a given function, now I can operate on options events. I don't need a whole set of operators for exactly the same as operate on ints to operate on options events, a separate names for them, and also like O star and O plus and O divided by an O minus or something like that. I don't need that. I could just map. I could just perform the map, and it will operate on options events. That's a very important point. And the same thing will hold true for try. So how is try different? Well, ladies and gentlemen, try is going to allow us to catch errors, to transduce errors, to take an error that is present in the form of an exception and to bundle it up so that we remember where the error was if one occurred, or otherwise carry around a value. Ladies and gentlemen, try and options are values. They are values that as we'll see, are called monads. They carry around an internal value, but they also can carry around optionally information about that value or information about other aspects of the context that gave rise to the value, etc. And Spark has an important role for these sort of monadic constructs, okay? It turns out we've seen others too. Stream, for example, is a monad. We'll come back to monads more generally. Okay, so let's go explore try. Now, for this part, be sure to import scala.util.underbar. If you haven't done that already, you will want to do so because try is defined there, okay? Okay, so we are going to use try here. Okay, there we go. Okay, so here's the try of a value. And the try of the value is just a wrapper for that value. Monads are normally just kind of wrappers. They're wrappers for things, but very useful wrappers for things. And in this case, it wrapped up the value 1, and it calls it success of 1. Remember with option, we had sum, like sum of S-O-M-E of 3, remember? Here we have success of 1, meaning that there was a success. There was no problemo. Okay. Alternatively, we could have a bad thing happen. Look at this. 1 divided by 0. Now we have a value still. It's a try value, but it encodes information about it. The nature, for example, of the failure that gave rise to it. Okay. Now let's take a look at this. Try 1 dot. Well, by analogy with option, in fact, analogy with other monads, what do you think we could do with a try? Let's map it. Let's square it, right? Well, okay, squaring 1 is, yeah, it's kind of beautiful. So let's square it. Okay. Here we go. There we go. Success of 1. Okay. What happens if what do you think will happen by analogy from the book and analogy from option? What do you think will happen when we square try 2? Square a failure. What do you think we'll get? We will get a failure. Okay. It's still remembering where the original, whence the original failure came. Okay. Where it came from, which it came. Okay. And yet it doesn't stop us cold in our tracks. We can get this error. We remember what caused it, but we can continue to process things in a structured way for later parts of a pipeline. Maybe we have, a pipeline that has 5 stages, and we composed it with another one that has 7 stages, and we get a pipeline that has 12 stages. And then we put that into a machine learning algorithm that uses that as part of the training. And then there's a component that uses the cross-validation components. These pipelines are often composed into larger pipelines. And again, we don't want to have to say, oh, there's been a failure. This website no longer responds. That machine is down. We have to stop everything, blow the whistle and stop it all and give up and go home and cry. We don't want to have to do that, right? So we instead want a way of handling things that is robust to failures at different points, allows us to proceed, but not proceed in a myopic way that just forgets that an error occurred. No, we actually want to record that an error occurred, what the nature of that error is, ideally where it is, etc. But at the same time, we want to let the other elements of the pipeline continue. And if this was just one website of thousands we were harvesting, just because one stinking website failed, it shouldn't matter. It shouldn't cause everything else to fail as well. Big data, we don't have that luxury. Big data, we might have, many sort of exceptional values that come up. Okay, now this is a little toy example, but let's again focus on this pipeline. Okay, so vector.fill, we're going to fill 100 elements of an array in a way that will build on the last thing. And we're going to fill each of them with a value from between 0 and 9 inclusive. Okay, so we call next int of 10 with 10, and that gives us a value between 0 and 9. Okay. Okay. So if you want to see what that looks like, you could do that here, and you get something like this, right? Notably, It does not include 10. It does include quite a few zeros. Okay? Okay. Maybe some of you can see where I'm going. Ladies and gentlemen, now I'd like you to map this to a value that, and where we will compute. Right, now we may need to put a type in place for this, but it may be okay there. Yeah. Okay. Yes. Here we go. So what's happened here? What are we getting out? Well, this is a vector. We filled the vector, we mapped it, and so what do we get out? We get out a vector. And what are the elements of this vector we get out? Well, they're 50 divided by, for the vector that's returned, each element is 50 divided by the corresponding element to the original vector, right? But what has happened in that process? Some were zero. And what did that lead to? Failures. It led to failures, ladies and gentlemen. So this vector we got out has lots of successes, but it had some failures. And those failures came about here because there were some original elements there that happened to be zero. And if you're operating with gobs of data, tons and tons of data, chances are there may be some outliers, some bad pieces of data, some irregular data, which don't fit neatly. And you get something equivalent to a divide by zero error or numeric exception or situation where it's an illegal value, etc. So this is not that unusual to be dealing with a situation where you have an error that occurs at this point, right? Okay, let's go look at this more. Now, suppose we want to square these values. What do we do more? What do we do? Sorry?
Map.
Yeah, we can map them, right? Now, mapping them is going to require a little bit more finesse here. Because each element now is a what? Is it an int? No, it's a try event, right? So how if we want to map them to, let's do an operator. Maybe we want to square them. Okay. Yeah. Okay. You folks might want to do something different. That's fine. If you're getting sick of squares, we could do rounds next time or something. No, we can do square root or something next time. Okay. Okay. So I want to map each of these, but I want to square each element. Can I just do x times x? Can I do that? Cannot. Cannot la. Yeah, that's darn right. You cannot. So why can't you do this? Well, you notice it says because it's not a member of try. So what's it trying to tell us? Well, you can't just take a try and multiply it by a try. And this goes back to our early values here, right? What if we wanted to multiply 2 tries, or for that matter, if we wanted to multiply 2 options, we never really talked about it. How would we? So I talked about how square can be lifted nicely by doing map. But earlier we had, do you remember we had these values V1, V2, V3? I think I defined a V3. Yeah. Do you remember that? This general principle holds true for, let's just see, did I define V1, V2, V3? I'm going to construct a little tuple and see so I don't, well, yeah, here we go. Remember I defined V1 to be sum of 3, V2 to be none, and V3 to be sum of 4. This was earlier. Okay, suppose I want to multiply V1 and V3. How would I do that? Or V1 and V2. How would I multiply them? Got to get you thinking about this. How would I multiply them? Can I just go like this? Can I do that? No. Why not? Well, it'll tell us the same thing. It'll say value is not a member of, well, yeah, here it said for try, here it said for this. What do I have to do? If I want to multiply them, how could I multiply these two values? I could use get. Great, I could, okay, I could use get or else. Suppose I use get. Okay, great, get. Let's say v2.get. What happens then? Boom. Dies. Boom. Died. Boom. So could I do that for V1? Yeah, I could do it for, but we want something that's robust for either. Now get or else, I heard Nell say it, and that's, I could use that, but then how am I going to handle, what do I do if it's, what value do I give it? What's the most distinguished what's the most distinguished int? So what would I do? I'd get or else, but what would the else be if I wanted multiplication to work? There's a better way, ladies and gentlemen. There's a beautiful way. There's a way of elegance and of power. Sorry? Okay, I could do pattern matching. That's true. I could do a match and a case for them. And that's not horrible, but it lacks the finesse, generality, and power that we will, actually, it has power, but it lacks the finesse and conciseness. Okay, ladies and gentlemen. Okay, so I want to be able to multiply two things, regardless of if any of them are none. We want it to be robust. We want it to be resilient. Even if any combination of these are none, we still want it to work, okay? We ready? Okay, how do we do it? How do we do it? Well, what thing works? What thing do we know works, regardless of whether it's none or some value? What thing works regardless if it's a success or failure? We can apply a certain operator, and get or else is one, but it's a good idea, but it turns out there'll be another way to make it more robust. That won't get us to where we want to go. How are we going to do it? What can we apply? I'll give you a hint. It has three letters. It begins with an M, ends with a P. Okay, ma'am. You folks know the story where my first programming class ever, I think I was about 10 years old, and our high school, I heard there was going to be a computer class over the summer. So I went to this high school. I was really scared. I was somewhere between 8 and 10. And they had these old PDP 11s over there, like the PDP 11. And they had this room with these terminals. And they had these big printing things of sheets of paper, yeah? And so we had a class, and all the other people seemed to be about like 10 times my age. They were like, well, okay, maybe not 10 times, but they were like at least twice my height, I think. And I was the only child there. I think I was the only person less than 25 or something, which was just like infinity at that time. And I was afraid. I remember one time I walked into high school and I saw these people welding, and I got freaked out, because they saw these sparks coming up. Anyway, so I was at this class, and I really wasn't paying much attention to the teacher, but I liked interacting with the computers, and I would go and sort of programming them. And then after like 4 weeks or something, or 6 weeks of the class, he said, "We're going to have an exam." I got so scared. I'd never been in an exam in my life, except maybe a physical exam, a physical exam. And so I got really scared. It sounds really scary, doesn't it? Like an exam, we're going to exam. But he said, "Don't worry, we're going to have a review session before the exam, and then we're going to have the exam." So I was sitting there. I sat in kind of the middle of the classroom, so he wouldn't look at me specifically. Hopefully he wouldn't notice me. And so then he began the review session, and he was going over each of the things that he had taught, each of the constructs and so on. This was, I think it was in Fortran, if I'm not mistaken. Anyway, he was going through and he was saying, you know, if you wanted to have a loop, or if you wanted to have a, you know, to add this to that, what do you do? Or if you wanted to create something that would do a job and you provide it a number and it will count up to that number, what would you create? Answer procedure. Okay. Anyway, so he was asking these questions. I just wanted to go touch the computers and start typing on them and creating a little program or something. So anyway, he walked back and forth, and then he said, if I wanted to do something from 1 to 100, I'm pretty sure this is the question phrasing was very similar to that. I wanted to repeat something, keep on doing it from 1 to 100 times. What would I use? And he was walking up and down the aisles like this, right? And he stopped in front of my thing, and he looked down at me. I looked up at him. He was much bigger than I was, and he was going to give an exam, and I didn't know what to answer. I just looked. I think I didn't say anything at all. Just look, stare. And he said, give you a hint. Begins with an L. It has 2 O's and a P in it. And I said, pool? This is absolutely true. This is absolutely true. I know exactly where this, you know, the exact place this occurred. And I think he gave up then. But fortunately, I didn't give up. Monads, ladies and gentlemen, monads. So when we have monads, we can apply a thing called map. It has an M, an A, and a P. And if you told me Pam, I'd be okay with that. Okay. Okay. So, ladies and gentlemen, map. How are we going to use map to perform a multiplication? Well, tell me, if map is none, can we perform a map? Remember what happened when we performed a map on a thing that wasn't none, right? We had this, and there we go. And it gives us back that. What if map were none? Would this be would that be okay to perform it on a thing that's none? Yeah. If Mark Twain were still around, he might call it the royal nonesuch. Look at that. There it is, right? Yeah, so it works. So it's robust to that. This is why this is the kernel of my idea. Let's use map. How else are we going to deal with it though? Suppose we want to multiply V1 and V2, but we want to be able to handle the case where either one is none. How could we handle that? Okay, right now we call get on this, and we know that can handle the case where V1 is none, right? That's what we just saw here. I mean, so even if what we call get, sorry, what am I doing? Get. Oh man, what am I doing? I just said map. What I meant to say is map. So if we do v1.map, we can handle the case where this is none. Okay, so what can we do here? Well, let me ask this. Suppose I were to say, I were to go something like this. Could I do this? Can I just do this? Can I do that? Cannot.
No.
Cannot la. Yeah, cannot la. Because what is V2? It doesn't know how to multiply a double by a option, or same principles hold to try. It doesn't know how to do this. So what could I do? I could say V2 dot what? Oh, we're thinking naively. I could say V2 dot get. But is that going to help us? No, because if V2 is none, what will happen? Bad things will happen. It will handle a case where V1 is, suppose So suppose I were to do this. Suppose I were to do that. Would it still work? Yeah, I don't know. Because it never even gets to this point. But suppose I were to say V1 this, and V2 is none. Will this work? No. Ladies and gentlemen, I need something. We're on the kernel of an idea, but what could I do? Oh, think about it. Oh, I won't give an exam. What could I do? Can I show you? Or do you have an idea?
Can you wrap it and try?
I could wrap it and try. Okay, that would be an idea. That would give us something. But actually, the truth is more beautiful than that. Yeah.
What if you said like v1.map and left the parameter blank?
Okay.
Like an underbar.
Okay. Yeah.
Times
Yeah.
another underbar. And it makes a function. Does that work? And then you have a.
Oh, that would be a nice thing. And in fact, there could be ways that could be rendered into a successful foray.
But not what you're thinking.
But not, no, actually, and what I'm thinking, it turns out has more generality, it turns out than that. So ladies and gentlemen, this is what, because it can be done for any number of different things. Watch this. So we know map works, right? We know map works regardless of the thing it's called on is none or an actual value. Same thing with try. You can call it on. So watch this. v2.map. Anyone want to complete the thought?
X to X.
Getting close. Suppose we want to multiply them. What are we going to do here? What is X? What is this? What is this guy?
V1?
He's the value inside of V1. If V1 is not none, if it actually holds a value, X will hold that value, the int value, right? It'll hold the int inside of the option event. What is Y here? What is that going to hold? The int inside of what? V2. Okay, so now I have the int that's inside of V1. I have the int that's inside of V2. What can I do with them? Yeah, X times Y. Okay, now, will this work regardless of whether these things are none? Suppose V2 is none, or suppose the first thing is none. Will it work? You bet it will. Suppose the second thing is none. Will it work? Yeah. Suppose that both are none. Will it work? Yes. Suppose that neither are none. Will it work? Will not? Will. Okay, sort of. We're very close. And ladies and gentlemen, now I will introduce a final key thing for you to know about. A thing called, unassumingly, flat map. Okay. Despite my hand motion, it's not flap map, it's flat map. Flat map. Flat map. Okay? And actually, what we're going to do is to be able to perform a flat map here. And the flat map is going to return us back a single value. And we're going to come back to flat map because it turns out it's more important than map. Flat map is, it turns out to be even more significant for some of our purposes than map. Okay, flat map. You can implement map in terms of flat map, but not vice versa, is my understanding, although I haven't proven it. So it turns out if we do this, things are happy. Okay, if we are doing if we have either one be none, the result will be none. If we have both be actual values, we will return values, okay, properly. So let's be clear. If V1 is none, flat map will return what? Anyone? What would map return? What would map flat map? And what would map return if we call it on none? It'll return none automatically. Short circuits it. Doesn't even do it. And it's the same thing is true with flat map. Okay. If this guy is not none, X will be bound to the value inside of him. Now this one, if this one is none, what will this thing return? It will return if this V3 here is none, what will calling map on it return? None, exactly. In which case, X will go to none, and we will return something that's a none. The problem was before, ladies and gentlemen, we returned nested values, like sum of this. Or if this thing were, then we do sum of none. But what we actually want is, we don't want a thing wrapped inside of another one. We want it all on the same level. And there's going to be some theory behind this, which we're going to talk about how this generalizes. So this is why we use a flat map. We don't want these nested structures. We just want, if this returns none, it's none. If a V1 is none, the whole result will be none. If V2 is none, the whole result will be none. If both are none, the whole result will be none. And if neither is none, we will get back sum of some value. Okay, so this is in fact how you'll in fact implement something where you want to operate on both of those. And it turns out that this is a general pattern that is true for monads more generally, and that is respected by some shorthand in Scala, okay, which we can use to really abbreviate things, because it's a bit of a handful to write. And as the final comments here, I will write the following, okay? So I'm just going to bring this down here. And I'm going to show different combinations of values here where you could see that this is a robust construct, okay? And we'll talk more about flat map next time, although I think the book might also go into it for the next chapter, okay? They didn't introduce flat map in the chapter you've already read, the chapters you've already read? Okay. Okay, ladies and gentlemen. So the way to write this in Scala in a more general way is the following. For X gets V1, Y gets V2, yield X times Y. If either is none, it'll be none. If both are not none, it will be some value. This is just shorthand for this. And in fact, it can handle a lot of things that I'm not showing here, like filtering of values, et cetera. It can handle loop situations, et cetera, associated with collections. But this basically just turns into this. The first one turns into a flat map. The first n turn into n minus 1 turn into flat maps. The last one turns into a map. And then there's some filtering ones, etc. So it turns out this is the same as that. Okay. So here we have try. Now, I think reflecting this, I think I'm going to talk next time about a little a broadening of this, whereby we use tries in a useful context where we harvest a set of websites, data from a set of websites, and some of them work and some do not work. And we'll have a pipeline that uses the information from them. And we'll use try and maybe option to have robust handling for the situation. Okay? Okay, so that's all we have time for today. There will not be an exam. So you don't have to worry about pools, okay? But it's good to get some exercise on this. Yeah, question?
Yeah, on the syllabus,
Yeah.
it says that January 25, there is the first deliverable project.
Oh, yeah, okay, okay. I'm gonna have to shift that. So I did start thinking a lot about project ideas. Maybe what I'll do is, I think we'll defer that a little bit. Thank you for pointing that out. I will defer that till this coming Tuesday, but what we'll do is next time I'll talk some about the project expectations, and I will see if I can raise some ideas for projects, okay? For then. They can be group projects, they can be individual projects, and we'll talk more next time about some ideas for them. Okay? Okay, very good. Thank you, everyone.